Welcome to the assembly language lecture on sequential logic. This is the digital logic series. We want to look at storage elements. So far, everything has been combinational logic, which means that the outputs depend on the current or present inputs. Only what right now matters. What you had a couple minutes ago has no effect. And in order for us to actually do things in a computer, we need to have storage elements, which means it depends on what we did before. So, holding previously computed values is used for this. We want to be able to save the state of affairs at the moment. There's actually, if we think about something mechanical, you can kind of understand there are two types of combination locks. The first combination lock is kind of like this. You know, you've seen these on your bike, and you get, as long as you do in 4184 and put those in the right placeholders there, it doesn't matter whether you dial in 4 first or 8 first or 1 first, as long as they're all lined up, it'll open. The values are important. The order in which they're set is not. Then there's this sequential type, you know, where you have to turn the thing around 2 times past this one and back left past this one and to that one and so on. That's the sequential kind of lock, and it depends on the sequence that the numbers were entered in, and it's much more difficult to pick. It's also an example of a memory storage device. So, bistability is the key to memory. When there are 2 stable states, you have a bistable circuit. Let's look at an example here. Here are 2 inverters, one right after the other, and this gives us a stable state when the input to the first inverter is a 0, the output to that inverter is a 1, that's the input to the second inverter, which makes the output of that second inverter a 0, and we feed that back into the first inverter, and that gives us a stable state. But there's actually another stable state that this could happen. If you notice the symmetry of the thing, you could move those inverters around, just move it up one and do wraparound, and the inverters would change positions, and so you'd end up with this kind of a thing. So there's really 2 stable states here. It will sit in either of these stable states forever. Well, the only problem with this example circuit we have here is we don't have a way to set which state it's in. We need that as well. Let's look at a reset set latch. And you'll notice this thing here has similar symmetry. It's actually the same on top and on bottom. These are actually NAND gates. This is the De Morgan way of writing a NAND gate here. But if you notice, if you were to draw a line right through there, it's symmetric. You know, you could flip it around that line, and you wouldn't know, except for the R and the S, that you really flipped it, and the Q and the Q not. It really is a symmetrical circuit. That means that's likely to have 2 stable states. So let's look at it. Here's one stable state. If I have the set and the reset as 1. And the Q is 0, and therefore the Q naught should be 1. So let's check and see how this works. If the set is 1, then this inverter right here makes a 0 at that input to the OR gate, which means the set has no effect. The same thing by symmetry on the reset. If the reset is 1, this inverter makes that a 0, so the set and the reset don't mess with anything as long as they're 1. So as long as set and reset are high, it's not going to have any effect on what the output is. So let's look and see how this could work. So suppose that the Q was a 0. If the Q was a 0, it goes through this inverter right here, this bubble, makes that a 1. The 1 is ORed with the 0 here to give me a 1 output. This 1 output goes back into this inverter here, which turns it into a 0. A 0 ORed with a 0 gives you a 0, and so it's stable. So now what happens if we lower either one, the set or the reset? Let's just try it and see what would happen, and see what happens to the Q and the Q naught. So here's the other stable state right here. I could just flip things around by symmetry. You know, this is also going to be stable with the Q here. A 1 and a 0, because you see, if anytime these set or reset are 1, those inverters right there make them have no effect on the ORs, and so, you know, by symmetry, you know, this is really that guy upside down. So if this Q was a 1, it's going to make that input right here a 0, and the 0 or 0 gives you a 0 for the Q naught, and it just, you know, it just works. So let's see what happens if we now take and lower one of that set or reset. So this is the stable circuit, I guess, and that's also a stable circuit. So let's try and lower one of these dudes. We're going to start with this guy right here, 1 and 1, and we're going to lower one of them. So we lowered the top one. If we lower the top one, this becomes a 1 right here on the input to the OR gate. A 1 or anything is a 1. So that's going to turn this 0 into a 1. The minute it turns into a 1, it makes this guy here a 0 on the input of this NOR gate. And so we have a 0 coming in here. Okay, let's see, a 0 coming in here, and we have a 1 coming into the input of this bubble, which makes a 0 here. 0 or 0 is 0, so this guy becomes a 0 right here, and so we have this, we just changed from the 1 0 state, or 0 1 state, to the 1 0 state by lowering one of these guys. So whichever one you lower is going to make that side go high and the other side go low. So let's put this 0 back up to a 1, and it will stay there forever. It will stay there forever, and that is really this other state over here. We just changed from one bistable state to the other. We can always, by symmetry, switch back by lowering this guy, which gives us back to our original thing. So that's a reset set latch. It's a bistable circuit that we can change to whichever stable state we like by using a couple of other inputs. That's the beginning parts of a memory, because now we can remember what the state was. You know, it tells us whether this guy was a 0 last or whether this guy was a 0 last by just looking at this reset set latch. So, and get back to a stable state, you want to keep both of these guys at a 1. Okay, so let's use that set reset latch to make a what's called a gated D latch. So if we look at here, this part of the circuit right here is our set reset latch. You know, it doesn't look the same schematic wise, but by De Morgan's theorem, this NAND gate is the same as the you know, these OR gates with the inverters on the input. That's the same using De Morgan's theorem. So they're really the same gate. So this is our old friend, the set reset latch. So we're using a set reset latch, And what we have is we have some one bit of data here. D is our data. Our data is coming in, and we'd like to save this data in this set reset latch. Actually, what we'd like to do is make Q here equal to that data, or whatever that data was whenever we set it. And how do we determine when we're going to set this thing? Well, this is the write enable right here, and when we make this guy, when we set this guy, and it will take whatever it reads on the data, and it will store it in this set reset latch, and Q will actually reflect whatever that was last time we pulsed the write enable. So let's look what happens. Suppose there's a data, D goes on here, right here, whatever it is, D is on there. And if we pulse write enable, what's going to happen? Well, this NAND gate is going to turn onto a 0 right here. Right before the bubble, it'll be a 1. Right after the bubble, it'll be a 0. If this data was high, if the data was high, it makes the set go low, and remember, when the set went low, it made the 1 go on top. So let's look again at that last time. When the set went low, whichever one went low gave us a 1 on top. If we made a low down here, we ended up with a 1 on bottom. So whichever one goes low is the one that's going to make the that side of the thing be a 1. So when this guy goes low, it makes Q go high, which basically, one way of looking at it is we just turned this Q to reflect what the data was if the data was high. Now if the data was low, then it will make this guy right here do what that guy was. So what would happen? We need to look and see what happens if the data is low to this guy and the data is high up there. If this is high, D is 1, then this will be low. A 0 or anything, and anything. 0 and anything is a 0. A 0, so you got a 0 just before the bubble, and on the other side of the bubble you got a 1. So this guy would be a 1, and that guy would be a 0. So whenever one side of this thing is a 1, the other side of this thing is a 0. Whenever this is a 0 here, this is a 1, and this part right here is all symmetrical. So if this D was a 0, then that guy will go high and that guy will go low. So basically Q will store whatever D was when we hit the write enable. So this is like a 1-bit memory. And you take this whole thing right here with this set reset latch and the 2 NAND gates and the inverter, and you put it all in one package and you call it a latch. It's a D latch. D is the data in, Q is the data from the last time we pulsed the write enable. So this is a D latch here, and that's an abstract symbol for that D latch. Normally they don't show you all this stuff because it's a lot more work figuring out what's going on with this, but once you've got the basic idea, you can say, oh, I see, I just know what this thing does because I've figured that one out. Now, if we took a whole bunch of these D latches, like if we took 4 of them here and hooked the write enable all together, and we connect each one of these latches to a separate bit of data, like D0 for this latch, D1 for that latch, and so on, and the outputs, we call this Q0 for this guy, up to Q3 for that guy, we can make a memory location. This is a 4-bit memory location here. And if you put all those latches together, we call that a register. And here is the symbol for a register. And notice this is a bold line here. It denotes that it is actually a bus, not just a single line. There's actually 4 lines in this fat line right here. And this is kind of a light line. And that indicates it's just a 1 wire. Registers are very fast memory. And normally the bits are labeled, the higher order bit on the left and the lower order bit on the right, kind of like when we're writing numbers. And so that's a register, and we use registers in computers quite a lot, you'll find out, and especially we'll be using them a lot in this class. Now, a memory is actually a collection of addressable registers. The address is a bus which tells which one of those registers you wish to read or write to. And so we have here an abstraction for a memory. Address is coming in, it's a fat line. Notice sometimes they put a little slash across it to say that there are n lines on that line, and this little slash says there are m lines on this bus, and there's m lines on that bus, and then you got a single line right here, which is the write enable. So basically what you would do is you would put on the address that you wish to read the memory location for, and you would, or maybe the address that you want to write it to. Suppose you need to write it first, so then you put the data you want to write on here, you pulse the write enable, and it'll store that on the queue. And if you want to read that, you just look at what's on the queue here. You don't have to mess with the write enable, but you do have to have the right address on the bus. Otherwise, you'll look at the wrong memory location. So queue always reflects, the contents of whatever data was whenever your write enable was enabled. And you can think of this thing as a collection of registers. Actually, usually registers are faster than most memory, but because there's several ways to do it, but let's look at one way to do it here. So how can we build a memory from latches? Well, there's 4 registers here. We're going to make a 4-bit memory. And so what we'll do is we'll put our address into this 2 to 4 decoder. So this right here is the decoder chip we looked at a while back, and basically you put on the address here, and it'll make, if this was a 1-1, it'll make that line go high and all these others go low. So this one and the write enable, when you write, if you pulse the write enable and you have the address of 1-1 on there, it will connect this register, and all these other guys will not get a write enable signal to their registers, but this guy will get a write enable to his register. And there's this D input. All of these registers have this data input to them, and this might be however many bits wide D is. This is a fat line, goes to all these registers. So when you write enable pulse this, you get you store all that D thing comes out on this Q3. Now, how do we make sure that the output right here is reading whatever your address is reading? Well, if you put in 1-1 on this guy right here, and you set it, this was a multiplexer. So if you put 1-1 on that address right here, it would select this input and connect it to that output, and then your output Q out here will actually be whatever's on the output of this Q3. If you change these addresses, it will change which one of these registers puts its output to the Q output. So there you have it. There's a 4 registers, 4 memory locations of D bits wide. So this is kind of a functional view of a memory location, and it basically has the same diagram that we looked at last time. Notice if there are 2 bits here, there are 2 to the 4 possible 2 to the 2 register locations, or 4 register locations here. So basically you get 2 to the n memory locations. Each of those memory locations handles m bits here. So really, they actually make things a little bit differently than what we just showed you up there. That would take up too much logic. They have a simpler way of doing things, and they arrange them in a matrix. And so what they do is they make a setup like this. This is a 4 words, 1, 2, 3, 4 words of 1, 2, 3 bits each. So notice this is a right here. This is one of those D memory latches, and so all of these are little boxes are the D memory latches. And you have your data, D0 here, D1, D2, D0 goes all the way, it's connected to all of these latches right here, all in parallel, and D1 is connected to all of these latches in parallel, and D2 is connected to all of these latches in parallel. And this is the write enable circuitry right here. This tells which word you're looking at. Actually, this is the addressing circuitry over here. So this line on the top is going to go high when you're looking at word 0. This line goes high when you're looking at word 1. This line goes high for word 2, and this line goes high for word 3. And only one word is high at a time. So if you look at this right here, they've made these gates so that only one of those is going to be high at a time. This guy has got no inverters on it, and this guy has 2 inverters on the input to that. So that makes it so that this guy goes high when they're both low there, but this guy down here goes high when they're both high. So that's the way that the word lines go. And now if we look at the outputs, that forms kind of a multiplexer here. If you look at only one of these AND gates is going to go high, and so it will allow the output from that guy to go to the output, for this column. One of these guys is going to go high, and that's what goes out to the D0. Or the Q0. This should be Qs down here. These Q0s as the outputs. So these columns here are like the multiplexer we just looked at. So how do you write one of this 12-bit memory? Well, there are write enable signals coming right in here, and then there's the addressing lines here. So suppose we set the addressing lines to be 0. That would mean we've selected this top line right here. We've selected basically these latches right here. When you hit the write enable signal, it will boom go down here, and it will write enable all these latches. So whatever's on the D signals will then be transferred out to the Q signals on all these latches. And likewise, if you're actually looking at the outputs down here, the multiplexer will make those outputs read out right after that. So that's how you write this 12-bit memory. So here's a quiz for you. I want you to look at this carefully. What is a bistable circuit? With an RS and AND latch, why can't R and S be low at the same time? Check it out. And then there's this latch right down here, which you should look at. And the question is, how can Q be set with the following latch? Right here. And you might also think, how did they dream this following latch up?